Hello everybody, my name is Dylan, and today we will be working through another implementation short with the topic being C++ linked lists. So this is kind of our first major data structure thus far, and as such it will be given the care that is needed. So let's go ahead and start our prompt analysis. We're going to be given some driver code. So we have the code in main that's going to take new numbers and put it in the linked list. So this is essentially building our linked list for us, and the way it's doing so is by prepending the nodes to the linked list, and we will talk about how exactly this works later on in the video. And this is just, we don't have to worry about this part, it's just talking about how the activity will be graded. So let's go ahead to step one. So we want to make a node class, which has two parts. The data part, which is an integer, and the pNext, which is a pointer to the next node. So this picture kind of demonstrates that. So if we have data 5 and data 6 for two separate nodes, then our linked list looks something like this, where these dots kind of just represent a null pointer. So you might be intimidated because it's saying, oh, make a class, but it's not like the classes we've went over so far. This is kind of just like a glorified struct. So what we need to do here, we just want to use our normal syntax for declaring a class, and then we want to give it some public data members. We want that integer data, and we want the node pointer for the next node in the list, right? So that looks like this. And so this looks a little weird at first. We might not have seen using an instance of a class as one of its data members before, but it's perfectly normal and it'll make sense as we go along in the activity. Some of the driver code that's been mentioned includes code to display the linked list. So we have the display number values function. So here's some sample output. So if we had created the linked list class correctly, then our output for running this function will look as follows. So let's actually take a second, and before we test this out and see if we've created our class correctly, let's just look at the display number values, or essentially displaying the linked list function here. So we can see it's a void function, and it's going to take in as a parameter a node pointer representing the head of the linked list. So the head is commonly, it's just the front of the list. So in our activity file over here, the head would be this first node right here. It would be the one containing data 5. So we're given that, and the head of a linked list will always contain, a singly linked list that is, will always contain all of the other nodes will be attached to it, if albeit potentially indirectly, right? So here we just take in the head as a parameter, and we're saying, okay, let's set some temporary node, the current node we'll call it, equal to the head pointer. And one little notational thing actually before I continue, quite often we will see pointers, their identifiers will have this little lowercase p prepending the name, and this is just to be absolutely clear with the fact that what we're dealing with is actually a pointer here. Especially in C, it becomes quite complicated when we're using a bunch of pointers to figure out what is a standard piece of data and what's actually a pointer to some other data. So we set this temporary data to our head pointer, and then we're going to say, okay, so while this node is not equal to null, when it's not pointing to no data, then we're just going to go ahead and print out the current data. And remember, we have a node pointer here, right? So we have to go ahead and dereference the pointer and then access its data, which is why we have this arrow operator. And then we just separate that by a space, and then we go ahead and advance the pointer here. We're saying, okay, we've already printed out the data for the first node, so now we want to go ahead to the next node in the list and repeat the process. So then we just go back up to the top, and it'll just print that out like so. So let's go ahead and see what that looks like. So that would be linked list P1. So as you can see, the main has some code for us that allows us to build the linked list. So we just want to enter all our values in, terminated by this sentinel value, -1. So let's just go 1, 4, 6, 3, 7. Why not? End with -1. So as you can see, the display number values function is going to go ahead and say, okay, the list number values are 7, 3, 6, 4, and 1. And so you might be thinking, okay, so why is the data backwards, right? We entered 1, 4, 6, 3, 7, the other way around. And the reason is because of what I discussed earlier, right? So we're prepending values nodes to the linked list, which means every time we add a new one, it's going to the front here. So if I were to add a new node to this linked list right here that has 5 and 6 in the example, and I wanted to add one with data 4, that node would be added right here, and then its next pointer would point to the previous head, and so on and so forth. So let's just go ahead and take a look at how the linked list is being built right now. So we have this temp pointer, and we have a null pointer to the head of the list. Right, so that's how it's being initialized here in the main. And then we're saying, okay, while we have not encountered our sentinel value, let's keep building the list. So here we're dynamically allocating memory on the heap for a new node, because we have that node class, so we can do it this way. And then we're saying, okay, set the data equal to what the user specified, and then set the next pointer equal to the previous head, and then set the head equal to the brand new node that we just made. So if we look at our little picture here, let's pretend we're starting with 6. So first we're making a new node. It doesn't have any data yet, so it looks like this. And then we're saying, okay, set the data equal to the user input, which in this case would be 6. And then we're saying, okay, set the next equal to the previous head. And for the first iteration, the previous head will be a null pointer, so it'll just point to nothing. And then we'll say, okay, we'll set the head equal to the temp. So now this is the head of the list, this node containing 6. And then we're going to read in some more input to repeat the process. So if we read in -1, then it will just end, and we'll just have a single a list with a single node, and it will just contain this data. If not, if we get some valid data, then we will just go ahead and repeat the process. So if we go back up, and we will say, okay, let's get a new node, and the data will be equal to the user input. So let's just say that is 5. And we're saying, okay, the next pointer, so this little block in the node, is going to point to the previous head. So now it's going to point to 6. And then we're saying, okay, well now we want the head pointer of the list to be the newest node, which is the front, since we're prepending nodes. And then the process repeats. So I hope that kind of gives us an idea of how this prepending operation works. Hopefully we'll get a little bit more into that in later activities. But for now, that should suffice to bolster our understanding. So awesome. We have officially created a node class in this small C++ program, and we are going to go ahead and continue to step 2. So in step 2 for this linked list activity, we want to just display the max of all of the numbers in the linked list. So we have to go ahead and implement this function that we have outlined here. So as we can see, we need to figure out what the return type is, we need to figure out what the parameters are. Right, so we can look at the function call in main to figure this out. So let's go ahead and refer to that. So if we look at get max of all numbers, we can see that it is embedded here within a print statement. So we can assume that it returns some sort of data, right? And we know we're getting the max of a number, so it should just be an integer, right? We have an integer linked list, so we should be returning an integer. And you can see as an argument, it takes the head of the list. So we're going to need a node pointer for the parameter for this function, and we're going to need an integer as the return type. So let's go ahead and get that in there. And it's, I think I have mentioned this before in previous videos, but we really want to be using the same identifiers for our parameters as we are using in our main function. We like this because it kind of fits together like puzzle pieces, and we can see that, hey, this data should definitely be being plugged into this function. So this might be really intimidating to try to implement at first. And what we can do is try to reference the function that we're given here, this display number values. So we just kind of iterate through the list here, and we're just printing stuff out. So commonly when we want to go ahead and process each node in a linked list, we'll just do this kind of thing here, where we're saying, okay, let's process the head, and then we'll advance it to the next until we reach the end of the list, which is denoted by a null pointer. So here, the operation instead of printing is we want to go ahead and find a max, and we can just use some simple branching to achieve this end. So let's go ahead and take a page from this book, and we're just going to say, okay, let's set this temporary current pointer equal to the head. And now we want to have the same kind of loop, so we're going to say, okay, so while this is not equal to null, And alternatively, guys, we can use null pointer. The distinction between the two is a bit subtle for this course, but just know that they work interchangeably for this case. I think null pointer is a bit safer though in general. Anyways, so we're going to go ahead and start this loop, and we're saying, okay, well, this is not equal to null. Then we are going to complete an operation. And what operation is that we want to complete? Well, we want to go ahead and find the maximum data in this linked list of integers. So we're going to have some data to represent this maximum, right? So we'll just initialize that max to 0 because we know, yeah, I mean, we're kind of assuming here that we have all positive numbers. If our integer list contained negative numbers as well, then maybe we would want to do something like negative infinity, which we would probably need like a macro for. But in this case, we'll just assume that we have positive integers. So if we initialize our max to 0, that means we know that there's definitely not anything less than this number for positive integers. So we're going to go ahead and say, okay, if we want to see if the max is less than the data in the current node, right? So in other words, we want to see if the current data, or if the data of the current node, so we have to access the data member of the node class, of this instance of the node class, using that arrow operator. You want to say, okay, if this is greater than the current max, then we want the current max to be equal to this data, right? So this is something that we've done many times before. It's just now contextualized to linked lists. And so now that we have done this assignment operation, we've gone ahead and checked if we have a new max within the data of our current node. Then we can go ahead and advance the pointer like we did before and repeat the process. So let's just go ahead and get some nice comments in here. Documenting our code is very important. Awesome. So it looks like we are just about done with this function, but of course we cannot forget that the whole idea of this is to go ahead and return whatever the max is. So we can just do that at the end. Our max will be appropriately assigned within this loop. Yeah, so, and then if we have like, let's consider the edge case of the head pointer being null. Well, then we would just say the max of all the data is 0, which means essentially that if we're assuming we have all positive integers, then since 0 is not a positive integer, 0 will indicate the fact that there is no data in the linked list. So it kind of works in all cases. Cool. So that takes care of the main two steps in this program. And now we want to go ahead and look at this slightly trickier extra credit problem. So we're given at least 3 nodes of data. So this is an important assumption that we are going to be using in our implementation here. And we want to just go ahead and delete the second node and return its data. Again, very important here. We're given a linked list with at least 3 nodes. So we just want to write this function. So if our linked list is this, if it has just the minimum amount of nodes, 3, and we want to delete the second one, then after deleting, it should look like this, where this node containing data 6 is just gone. So how might we accomplish this? Well, first of all, let's just consider our return type and our parameters. So we know that we want to return the data in the second node, and we know that the data in these nodes of this linked list contain integers. So we have an integer return type. And then just like most of these other functions here, we will be having the head pointer as our parameter. Because, well, I mean, first of all, we can just go ahead and look at main, and we can see that the delete second node takes the head pointer. But if we didn't have that information, we could think about, so how exactly are we going to access members of this linked list? How are you going to access various nodes? And you can access any node through the head pointer. So that's why we're going to be passing it here as our parameter. So what do we do? Well, we know that we want to return the data in the second node. So I think a first good step is just to go ahead and save that data. Especially since we're going to be having to take memory or deallocate memory from the heap. So we're going to need to save that value here. So we'll just say an integer second data is equal to so we're taking the head pointer, And we're saying, okay, go to the next node in the list, take the next pointer of the head pointer. So this refers to the second node. And then we're going to dereference this pointer and access the data contained in that node. So if we look at our example list over here, we have this list of 3, then second data would just refer to this 6 because we're saying, hey, let's look at the head, then let's follow its next pointer to the next node, and then let's look at the next pointer's data, right? So its integer data contains 6 in that case. Okay, so now we just kind of want to, there's a bunch of ways you can go about this, but the most efficient way to do this is just to kind of reconnect the pointers and then delete this node. Right, so it's kind of hard to illustrate here, but if you follow my cursor, we can see, okay, so we have the head pointer here. It has data 5. And what we want to do is we just want to make this next pointer go all the way over here to 4. And then we just want to completely eliminate this node by using our delete keyword, right? So if we want this next pointer, if we want the next pointer of the head pointer to point to what is currently the head's next pointer, then we will have to do just that in our code. So we'll just say, okay, let's shift this pointer, and to do so we're going to say the next pointer is going to be equal to, so the head's next pointer, I know this is a lot of word vomit here, the head's next pointer, this arrow, is going to be equal, or is going to go ahead and point to what is currently pointed to by the second node. Right? So in this way, we're kind of circumventing the second node and just reconnecting the linked list. And at this point, our linked list restoration is done. Our second node is no longer part of our linked list. However, we want to avoid a memory leak, so we're going to have to deallocate the memory off the heap. So we're going to just use this delete keyword, if I can spell it right, and we're going to go ahead and delete so we will actually need a variable to store our second node, right? Otherwise, we're not going to be able to deallocate the memory from the heap. Think of it as sort of like a temp variable, right? So we'll say we have a node pointer p second, and that will be equal to p head, p next, and then we can just use p second here to kind of shorten up our notation. Right, so we're storing the data in the second node, and then we're just going to say, okay, after we've reconnected all this stuff, we want to delete p second. So let's go ahead and go over this one more time. So the first thing we want to do is we want to get a variable for our second node in the linked list, this guy right here in the middle, and then we're going to store its data using this arrow operator, and then we're just going to shift the pointer over to the next node, and then we're going to finally go ahead and delete this dangling pointer in the middle. And that's all there is to it, guys. So linked lists are, I would say, pretty intimidating at first. They can definitely be scary, kind of hard to visualize. So this is when diagramming becomes very, very, very important. We need to draw lots of pictures. We need to understand what's going on. And that's kind of the best way to do it, is to draw lots of these little boxes with one having the data and then one just, pointing to our next node in the list. So yeah, guys, I think that about covers it. And if we want to go ahead and test everything we've worked on, we can look at the output for the final solution. So we want to enter list numbers separated by space. So let's go ahead and let's first try a linked list with just 3 nodes. So we'll say 3, 5, 2. -1 for our sentinel value. We can see, okay, so the list number values are this, prints out our list, then the max is 5, so that is correct. And it deletes the second node, so the data of the second node was in fact 5, and now the list contains just 2 and 3. So one thing to note real quick actually about our last function here is that here, this approach, the way we're doing it, will only work if we definitely have at least 3 nodes in our list. Otherwise, we're going to get seg faults, and it's not going to be fun. So what we should do before we kind of take care of any of this code is we should check if the head pointer is null. If the head pointer is null, then we can just ignore any of this because there's no second node to delete. So you would just kind of wrap all of this in an if statement that asks, hey, is p head null? And then, yeah. So that takes care of that. Oh, and then also, forgot to type it in here, I want to go ahead and return second data. So the reason the solution worked here is because it was actually referencing a different file. Let's go ahead and test our solution with a slightly larger linked list. So we'll have 3, 7, 8, 4, 2, and 6 terminated via sentinel value. And as we can see, it'll go ahead and do everything we've already tested out properly. It gets the nice max, which is 8, and sees that the data of the second node in the list is 2. And then it'll just remove that, remove the data, remove that node entirely, and go ahead and print out the list again. So yeah, guys, linked list, a little bit tricky, but you'll get the hang of it. It just takes a lot of practice. And yeah, I will see you guys in the next video.